I think I set a personal record today. My materials were actually loaded on the computer 15 minutes to air. Now let's see if they're worth anything. So I'm going to be talking about mask filters in channel 14 and a bunch of different aspects, and I've got a lot of materials, so I'm going to run through it as fast as I can, and maybe there'll be time for questions later. A lot of this started due to some empirical experience that was gained at Sutro Tower. In the early days, some stations experienced reception problems while others didn't, and some studies were done to try and figure out why. And it turned out that those stations that had six-pole had neighboring stations, adjacent channels with six-pole filters, had reception problems, and those that had neighbors with eight-pole filters did not have reception problems. And so Sutro established a new policy, and still in effect, that says only eight-pole filters are allowed. But why was that necessary? And that experience and having to put a transmitter in there with an eight-pole filter is kind of what led to what you're about to see. So at the very basic level, mask filters are used to control adjacent channel interference. The FCC rules, of course, specify a spectrum mask that defines limitations on out-of-channel emissions. And those emissions come from amplifier nonlinearities that generate intermodulation products. Basically, mask filters provide protection to other stations. They don't help the station itself, they help your neighbors. And the station cannot protect itself from adjacent channel signals. Those adjacent channel signals, when they get into the adjacent channel, become co-channel interference. And co-channel interference cannot be filtered. So we can think of mask filters as good neighbor filters or good spectrum citizen filters. And neither a filter at the transmitter or a filter in a receiver can help overcome emissions that occur in that adjacent channel or those adjacent channels. When we look at mask filters themselves, there are different kinds. These days you can get them retunable between channels or fixed, so not retunable. We can get them sharp tuned or not. There's a trade-off between selectivity and losses. The primary filters used are 6-pole, 8-pole, and 12-pole. With a 6-pole filter, we get lower selectivity, but also lower losses. The 6-pole filter tends to roll off into the adjacent channels, and we'll see that in a bit. The 8-pole filter, on the other hand, has higher selectivity, but also slightly higher losses. The difference is about 1/10 of a dB. An 8-pole filter has sharp nulls at the channel edges, as we'll see. And a 12-pole filter, we'll talk more about that when we get to talking about channel 14. One of the things that I did to try and understand what was going on in Sutro Tower is to build a model. And I'm going to show you a bit about that model. The model is essentially a representation of the spectrum many times over. And that representation looks at 120 samples of the spectrum per 6 megahertz channel. So there are 50 kilohertz samples of the spectrum, and essentially looking at the power in those portions of the spectrum, and then looking at what happens to that power as we generate intermod products. So you'll see coming up that I've done a number of spectrum plots based on those power analyses. Each of the matrices involves 121 points in the channel. You square that, you get 14,641 IM products for each IM order, and we'll be going through that. So when you look at this whole analysis, there are over 100,000 spectrum samples that are involved. And in doing this, what I've done is to set up the levels of the intermod product orders based on the spectrum spreading, and I'll explain that as we go along. And one other thing, in order to make it more easily understandable in viewing, since I'm doing this on specific sample points, and otherwise there'd have been a lot of wild variations in some areas of the plot. I've used a 5-point smoothing filter on the data, which will make it easier to understand as we look at it. So here's the upper left corner of one of the matrices. It's much larger. As you can see across the top, it goes every 50 kilohertz across the spectrum. So the first value is 5. This is channel 35, I guess it is. Channel center at 599 megahertz. So it starts at 596, the next one's 596.05, 596.1, and so on. And then going down the left side, you see the same thing. And so those are the starting frequencies for producing the products. And then in the middle, you see each of the products. So part of what goes on when you generate intermod is that you have, if this is the spectrum of the channel, and this is what we're looking at here. So here's 596, and here's 602, the ends of that channel. Every point in the spectrum here intermodulates with every other point in the spectrum. And so that's why with digital signals, where we have a broad spectrum of power, we tend to have intermod products that are produced that go out in smooth spectra, where when we were doing this with analog signals, you'd just get the individual carriers that would intermodulate with one another. And by seeing where the product ended up, you could tell what components were in it. We don't have that luxury anymore with digital signals. You only need one transmitter to cause intermod, where in the old analog days, you needed multiple transmitters to generate intermod products. So what these matrices do, essentially, is take every frequency and multiply it in a particular way by every other frequency. And you can see that where the two are the same, there's no product produced, because that's on that particular section of the spectrum. So with that as background, here is an example of third-order products in a linear space presentation. So this says that third order, so it's 2 times one frequency minus the other, total of 3. When I talk about fifth order, that's 3 times one minus 2 times the other. Seventh order, 4 times minus 3 times. That's what we're looking at when we look at these spectrum plots. As I say, this is linear space. Here's what it looks like in log space. So this is in dB. And this is the way most of us are used to seeing it on spectrum analyzers. So here's the third order, and here's the fifth order. Notice that the third order covers 3 channels. The channels are shown by the tick marks at the top here. So a third order will equal 3 channels, a fifth order will equal 5 channels, seventh order 7 channels, ninth order 9 channels. Okay, and so all of those are being generated inside the transmitter amplifiers primarily. And what happens then when we sum all that up, and while we're at it, let's put in the original signal, we end up with a spectrum that looks like that. And that's essentially what comes out of the high-power amplifiers in a transmitter. And you'll notice that these don't seem like they're on the levels that you probably remember. The shoulders have to be 47 dB down from channel power. But channel power is up here, and because we're using a 50 kilohertz bandwidth, think of it as a spectrum analyzer resolution bandwidth, in order to look at this, the flat top of the signal ends up 20.79 dB below that. If you add up minus 20.79 dB of power 120 times, you're going to get 1. It'll come to unity. And that's up here at 0 dB. So that's why we have that separation. And then if we start with 47 dB down in the first, 47 dB down in the first 500 kilohertz, which is what the FCC rules say about where the shoulders have to be. If we want, since we're talking about 500 kilohertz, that's 10 of those samples. 10 times the power is 10 dB. So what that says is that we can expect to find each of the 50 kilohertz samples at minus 57 in order to end up with 10 of them being at minus 47. And so that's why this is showing here at minus 57. So that's the signal that we're starting with coming out of the transmitter. Then what are we going to do with it in order to meet the FCC rules? Well, one thing we can do is to apply a 6-pole filter, which looks kind of like this. And by the way, I've gone to filter manufacturers and gotten the real data on real filters, and I've selected one of them to act as a representative here. And you'll notice that in a 6-pole filter, the channel edge is there, and the roll-off starts a little outside the channel and ends up down at about minus 55 or so, almost a channel away. And we'll see what that does to our noisy, intermodulating signal in a minute. And the same thing happens on the top side of the channel. Now, if we look at an 8-pole filter, you'll see that it starts down almost immediately at the channel edge, and it has a null right adjacent to the channel edge, and a little return. It comes back up to minus 20, and then it drops way down, and it's below 65 halfway across the next channel. So it's quite a bit sharper than that, and just going back and forth, you can see that that's going to have some effect on the amount of power that's impacting the adjacent channel. So now let's put all that together, and let's add a 6-pole filter to our noise spectrum, and we end up, if you add the channel power from the edge of the channel there at 596 down to the edge of the next channel at 590, you get minus 47 dB. With this typical filter. And by the way, this spike here is something I put in intentionally just to set off the two sides of this. The data that I was provided ends at this spike, and just to have continuity of what you're seeing, I then just put in a continuation, essentially a linear continuation of the roll-off that began before that point, just so it looks reasonable. But the real data ends at this spike, and that'll be constant throughout these images. So and then here's the 8-pole filter, and you can see that the total from here to here is minus 57 dB of the power in this channel, essentially up here. And again, this flat top is 20.79 down. So now it looks like a page is missing. And I know I did that, so I'm going to have to try and talk through that. Apparently it didn't get saved onto the USB stick. Problem of late delivery of the materials. What can I say? So when we look at the choice between 6-pole and 8-pole filters, experience says that 6-pole filters have been problematic in the past even though they meet the requirements of the FCC rules. So how do we decide which is the best to use? Well, for one thing, the spectrum was a lot looser, if I can call it that, when those rules were set up. We did not have as many stations side by side by side. We also had personnel who knew what they were doing in RF plants, which in some cases we do now, but in a lot of cases we don't. And so we could expect that the maintenance of the transmitters was better and would be better in bygone days. So what do we do going forward? Well, it turns out when you do all the math that if you have a station that's in the area where it's close to the limit on what's allowed for adjacent channel interference, and then on top of that, it has the power that comes out of a 6-pole filter, you start exceeding what will cause interference into a receiver, even though it technically meets both requirements. And so if you want to avoid the problems that they found at Sutro, then an 8-pole filter will fix that because it gives you a 10 dB improvement on the amount of what I'll call co-channel adjacent channel power. It's the power that a station leaks into the adjacent channel that becomes co-channel. So if we're in situations where we've got a dense spectrum, then 8-pole filters make the greatest sense. And if we're out in the boonies somewhere and there aren't too many stations around and they're not likely to be side by side, then a 6-pole filter is probably something you can get away with, but even there, if the station can afford it, and it's not a huge percentage on the cost of the filter, then still an 8-pole filter is a better choice. So let me continue on now and start looking at channel 14. Turns out that many of the issues that come up when we're talking about the mask filters for stations elsewhere than channel 14 apply as well on channel 14. But we have even more considerations here. To start with, just for the baseline, channel 14, as a reminder, is 470 to 476 megahertz. The land mobile service goes from 450 to 470 megahertz. So there is no guard band between a service that can be delivering 1 megawatt on starting at 470.001 megahertz, and another service that can be looking for a 1/4 microvolt signal at 469.9995 megahertz. And yet we have to provide protection for that. So this gets to be a bit dicey. To think about what the fundamental characteristics are, the receiver threshold for a 1/4 microvolt is minus 119 dBm. If we have a receiving antenna gain on the order of 6 to 13 dB, which would be typical for land mobile kind of reception, that pushes the threshold down to minus 125 to minus 132 dBm, effectively in the air, if you will. On top of that, there's an FCC mandate to protect land mobile radio service reception. That's always been there, but it's never been worded the way it is on current construction permits. If you look at the condition on a repack channel 14 construction permit, it says, and I'm going to read the parts that I bolded here, during equipment tests, permittee shall take measures to identify and eliminate objectionable interference which may be caused in the 460 to 470 megahertz band. Documentation that interference will not be caused shall be submitted. Program tests shall not be commenced and may only be started after specific authority is granted by the Commission. So unlike in the past, where program test authority was automatic when a facility was built, that is not the case this time for Channel 14. We have an obligation to go out and prove and document that no interference will be caused. That's what that condition says, and it's on every Channel 14 CP authorization that I know of. So let's look at some of the other considerations about Channel 14, and we'll come back to that condition in a minute, a couple minutes. So what are the sources of Channel 14 interference to land mobile? For one thing, transmitter emissions, and we can mitigate those by use of transmitter filtering, the mask filter. Receiver front-end selectivity, and we can help that with better receiver filtering. But also something that if you've been coming to these conferences for a while, you've heard me talk about in the past, passive intermodulation. That you cannot fix with a filter. That has to be fixed at the source. It's just like I was saying a minute ago about the mask filters and receivers. You know, once the energy's there in the adjacent channel, that becomes co-channel interference on that channel and cannot be fixed with a filter. So let's look at the interference threshold to land mobile, because this is what we're going to have to be actually using in the field. Generally, interference modeling considers that interference occurs when the noise floor of an interfered with station increases by 1 dB. That's equal to the addition of minus 5.9 dB of noise to the noise floor of that channel. So almost 6 dB. If I've got a signal with a signal level of 1, I'm essentially adding roughly 25%, just slightly over 25% more power to that channel. That'll be a 1 dB increase. So that means that the interfering signal must be less than that noise floor minus 5.9 dB. That's our target. And if we look at the noise floor of a 12.5 kilohertz channel, which would be a typical land mobile kind of bandwidth, the old formula for noise, the noise floor of a channel is KTB, Boltzmann's constant, times the temperature in Kelvin times the bandwidth in hertz. And that comes out to be minus 133 dBm, making the interference threshold minus 138 dBm in a 12.5 kilohertz channel. So now we come to mask filters for channel 14. This is a typical 12-pole filter, and it's got some unusual characteristics if you're not used to looking at channel 14 filters. The channel edges are here and here. I hope you can see the white lines that are there. So upper edge, lower edge. The behavior on the upper edge is kind of like what we saw with the 8-pole filter, where right at the channel edge, it's starting to head down, and then you end up with a first null a little outside the channel edge. And so you get the full energy from that channel through the filter with only a slight bit of attenuation, and then you drop off precipitously. In the case of the lower edge of the channel on channel 14, this marker is where the ATSC 1.0 pilot is. And so what's happening here is that the filter starts to drop precipitously just below the pilot, and you're essentially cutting off the lower sideband, the vestigial sideband that's below that pilot, with the objective of having a first null right at the channel edge, so that you get a very sharp reduction and a very small minor lobe coming back up. And so from the edge of the channel 14 signal downward, this filter does not exceed about minus 55 dB. And you combine that like we did earlier with the intermod products, and you'll see that that is down in the minus 100 and something range right away. Unlike the typical mask filter where you have to be down 110 dB from channel power 6 megahertz away, that is one channel away, you have to be, in order to protect land mobile, you have to be down much more quickly. Now, even if we do that, that's not going to solve all the problems. Remember that the next thing that I mentioned was passive intermod. And I call this passive intermod redux because we're going over again stuff that I've shown in this conference several years ago. So, but just for those of you who haven't seen it, passive intermod, or PIM, is well known in cellular and PCS and those kinds of services, and it results from nonlinearities that occur after the transmitter. They occur in systems or the environment. In some cases, they're intentional conductors, for instance, transmission lines and antennas and the like, that are part of this actual system, transmission system. And those are caused by metallurgy issues, dissimilar metals and wrong kind of plating, things of that sort, connectors that are not cinched up tight enough. And then there are unintentional conductors like connectors and transmission lines and antennas and stuff that are nearby on the tower or near to the tower. You can have, for instance, chain link fencing that's gotten rusty. A lot of the problems with PIM are caused by rust and corrosion in the environment. And we'll see that in just a second. Basically, if you want to remediate PIM, it requires that you remove it from the environment of the system. Either you have to fix the system itself, or you have to fix the components around the system, like peeling the layers of the proverbial onion. And there are lots of sources of PIM, and you can't always tell which one is causing your problem. Sometimes a 5-pound rubber mallet will do it, applied judiciously. And literally, if you listen with an appropriate receiver, like a spectrum analyzer in zero span mode, and then bang on the tower, you can find sometimes where the PIM is, just by listening to the AM of the noise. But it's impossible to know in advance which sources are making what contribution. And so in many ways, it requires a scattershot solution of just dealing with everything. So here's some examples taken in the last few months. Those of you who saw my presentations before, I've shown pictures like this in the past. This is a tower that currently does not have channel 14 on it, but is slated to have a new channel 14. And this is what we're starting with. I mean, this is rusty bolt syndrome in spades. Threaded rod into a coupling. So right there you have two many diodes in parallel kinds of connections. Here's another one, the so-called rusty bolt syndrome. Here's a connector that's not properly attached to its cable anymore and is loose on the socket. Here's an example of an appurtenance that on a tower that's holding some equipment up that's all rusty. All of these are potential PIM generators. And in fact, and here's one more. I'd never seen this one before. This is a grating, it's like an ice shield over a bunch of heat exchangers. And if you look closely, all of those heat exchangers are showing rust everywhere, which is basically being blown down from the grating up above. In fact, that screen shows it even better than what I'm seeing here. And so we made measurements on this tower. And for those of you who remember my IM lobe technique, it did show PIM. And it was at this stage only locatable on the tower, but it's expanding, it's coming. So how do you deal with it? Basically stainless steel everywhere, 716 DIN connectors instead of type N connectors, all those kinds of things. Then there's the problem of reception. we need different solutions if you have a single receiver connected to a single antenna than if you have a master antenna system. I've drawn a little diagram here that shows what you do in a master antenna system and where the filters have to go to notch the edge and tune out or subtract channel 14 and then do proper amplification. Then there are a couple other aspects of this. One is that with the new condition in the construction permit, there's going to have to be notifications done. There will have to be notifications done to land mobile operators. They're going to have to be found, and then steps are going to have to be taken to visit their sites and determine whether or not they have interference, and then remediate it if they do have interference. So there'll have to be site visits, probably 2 at each site, seems like. That means contact with the operators or licensees. It implies the use of the ULS to locate those operators. In the case of that tower that I just showed you, there's somewhere between hundreds and thousands of land mobile operations within a reasonable distance of that tower. What is a reasonable distance? That's one of the things we have to determine. In any event, it implies that there's going to be a need for a long test period because somebody's going to have to be at each one of those sites to measure the 1 dB change in the noise floor, and the only way you're going to find that is turn the transmitter on and off. Well, that's going to have to be before the station's in use. I'm expecting to see STAs for all of those channel 14s to lengthen the test period. Also means a large number of personnel and a lot of time at each site. It also means that there are going to have to be interactions with the land mobile operators. We're going to have to understand the configurations at each installation, determine whether or not remediation is necessary and what equipment to use, and put it in and test it, and then probably have a means to communicate with those folks after the fact, well, before and after, to set up appointments and deal with any complaints. And one of the thoughts for that is possibly to use a website to manage interactions. There's at least one company that's preparing to provide all of those services. So in summary, mask filters, we have 6-pole versus 8-pole. 8-pole filters are 10 dB better. In the congested spectrum, they really help. Stations cannot protect themselves. They can only protect their neighbors. So that means you need to protect your neighbors so that you can then say to your neighbors, be a good neighbor and protect me too. All must protect one another, basically. And you can look at the investment in an 8-pole filter as a one-time purchase of an insurance policy. For channel 14, the issue is to protect land mobile. There are three sources of the interference: the transmitters, PIM in the environment, and receivers. Transmitters and receivers can be treated with filters, but PIM means cleaning it up the environment. And interactions with the land mobile operators will be part of the process. And that's it. Thank you.